Hi, everybody. Now we're doing chapter 3. Yay! 3.1, and this is about the constant E and continuous compound interest. And we'll see the connection between those two things. First of all, the number E is a number. It's basically it's a number, and it's approximately 2.718. And E stands for Euler, Euler. And Euler was one of the first people to really develop and use this number and all kinds of cool things. So it's named E in his honor. Who is Euler, you ask? Funny you should ask. I'm going to show you. Leonhard Euler was a great mathematician, very great mathematician, who just did a ton of math stuff. That constant 2.718, which sometimes referred to as Euler's constant, is named E in his honor. So, and that is probably the second most famous constant in math. I would say that pi is probably the most famous of irrational numbers. I mean, of the irrational, probably the most famous irrational number. The second most famous, pi is probably the most famous, and E is probably the second most famous. Either way, E, even though it's an irrational number, 2.718, blah, 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 believe it or not, when it comes to calculus, it's actually makes things easier. So I guess the E also stands for easy. That may not make a lot of sense right now, but it will make sense as our course develops. Doing things with E, doing things base E and stuff like that is actually going to make calculus easier than doing things in base 10 or whatever. But we'll see. That's going to come as we go. Anyway, that's Euler. So let's go back to our lesson. Okay. So let me get my picture out of here. Again, having this, sometimes wherever I put myself, it gets in the way a lot of times, and I have to keep moving it around. But I keep it up because I want you to see, I want you to realize I'm a human being. I actually am a human being. By the way, I put my phone number and email and all that stuff. I put that on Canvas. So yes, I am here, and I'm a human being, a real person. And you can call me anytime. Students often call me. We could talk on the phone. We could make a Zoom, whatever meeting. You could email me, whatever. You know, I'm actually here live. This class is not just being taught by a machine, and it's not like just something which I put, online 20 years ago, and now you just come into this thing, and it's actually a live thing. Okay. Anyway, the number E is defined as this limit. The limit is n goes to infinity of 1 plus 1 over n to the nth power. Or I could say it this way: the limit is s goes to 0 of 1 plus s to the 1 over s power. If you notice that this and this are really the same thing, and because the reciprocal of something going to 0 goes to infinity, and so on and so forth. Okay, blah 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 blah. Continuous. Now, what does this have to do with continuous compound interest? Funny you should ask. And another question you might want to ask is, what is continuous compound interest? Well, the answer is continuous compound interest is found with a formula that uses the constant E. And A is equal to P times E to the RT. I always remember this as PERT. P stands for the principal. That's the guy in charge of your school. No, I'm just kidding. P stands for the principal, which is the amount of money you clunk down. E is that number, 2.718. R is the annual interest rate, and of course you have to write as a decimal. And T is the time in years. So it's a number of years. So which means that if it's 5 years, T equals 5. If it's 6 months, T equals 0.5 because it's half a year, and so on and so forth. Anyway, if $100 is invested at 6% compounded continuously, what amount will be in the account after 2 years? How much interest will be earned? Well, we're going to use A equals P times E to the RT. P again is 100, so it's $100. 6% is 0.006, and it's 2 years, so it's times 2. And if you crunch it out with a calculator, you get 112.74. So it's roughly, that's how much money you got. That's how much money will be in the account after 2 years. How much of that was interest? Well, obviously you started with 100, so you have to subtract off the original 100 and $12. So you've made 12. Well, it's not a lot. You've made $12 of interest, and it's only over $100 investment, so that's not so bad. That's actually pretty good. So it is So that's the story. That's it. You've done it. Yay. And we used E. And again, E is usually on a calculator. Every calculator is different, but usually the calculator will have a button for E or something like that. And if it doesn't, you can just punch in 2.71828, whatever the numbers. Alrighty. Let's look at another example. Oops. Oopsie, went too far. Okay. Graphing the growth of an investment. So Union Savings Bank offers a 5-year certificate of deposit that earns 5.75% compounded continuously. If $1,000 is invested in one of these CDs, graph the amount in the account as a function of time for a period of 5 years. Now we want to graph A equals 1,000 times E to the 0.0575 T, and T goes between 0 and 5. So basically I could do this on Desmos, but they do it for us already down here. And we basically get this little thing here. Now this looks like a straight line, but it's not really a straight line. It's actually a curve. It's an exponential curve. Even though it doesn't appear that way based on, because this is only a very small part of the graph. Just like if you look at a small part of the Earth, you think the Earth is flat, but if you look at the entire Earth, you see the Earth is really round. So there you go, we did it, yay. Okay, let's look at example 3, because we did example 1 and example 2. I think we should follow it up with example 3. Computing growth time. How long? This is a slightly different question. How long will it take an investment of 5,000 to grow to 8,000? See, before we were saying you put in 5,000 and you wait, 2 years. How much money are you going to have? Now we're saying you have 5,000. Eventually, it's going to become 8,000. How long is that going to take? Assuming you get 5% compounded continuously. So what you're going to, so in other words, what you're really doing here is you're taking this equation. A, that's the final balance of 8,000. P, that's the initial balance of 5,000. R is the 5% interest rate. So basically, you're solving for T. How long? We're solving for T. That's basically what we're doing here. So 8,000 equals 5,000 times e to the 0.05 t. And now I divide both sides by 5,000, so I get e to the 0.05 t equals 1.6. Now what I do is I want to get rid of the exponent. So I take the ln of each side. And when I take the ln of it, basically the ln and the e, ln is logarithms base e. And the ln of e to a power basically sort of cancels out, just like having a humidifier and a dehumidifier in the same room, I guess. And I'm just left with the exponent, 0.05 t, and that equals the ln of this side, which is ln of 1.6. Now, the ln of 1.6, that's just a number that you could crunch out on a calculator. So to get t, all you gotta do is divide both sides by 0.05. So t is equal to ln of 1.6 divided by 0.05, which if you crunch it out on a calculator, it turns out to be 9.4 years. So if you so you have $5,000, but you want to have 8,000, so it'll happen in 9.4 years. And another thing which you could also do, this is interesting. You could on a graphing calculator, you could put in this graph, the A equals P or T graph, and you can also put the graph of just Y equals 8,000 and see where the two graphs intersect. That's interesting. That's a very interesting way of doing it with a graphing calculator. How long will actually? What? I like that. I want to let's do that now, just for. I'll show you. If I go to Desmos, this red graph is the Y equals 5,000 e to the 0.05x, and this blue horizontal line is Y equals 8,000. I had to really shrink this graph a lot because to fit it all in, and I'll do this, but it's not going to do that much. This won't do all that much. How much that's really going to accomplish by doing that? Anyway, so now it's really hard to see where they intersect, with the naked eye because this is so small. But with Desmos, you can click on the and it gives you that's the 0 is the y-axis, but I want to go to the next thing. Let's see if I can get. Oh, here we go. All right, had a second ago. So this is with the two graphs intersect, 9.4 comma 8,000, which means that 8,000 is the y value, 9.4 is the x value, which the x value is time. So it's going to take 9.4 years to reach 8,000. So it's just another way. So you could do it with logs, or you could do it with a graphing calculator by actually drawing the graphs. So you have a couple of ways to do the same thing. Kind of cool. Anyway, let's move on. And let's look at example 4. Computing doubling time. How long will it take money to double if it is invested at 6.5% compounded continuously? Notice that they don't say how much money. Is it $1,000? Is it $5,000? Is it $100? Well, it doesn't really matter because doubling it takes the same amount of time. All the money doubles, whether it's $1 million or $100 or $2. It doesn't matter. So let's look here. Oh, they say the best way to double your money is to fold it up and put it in your pocket. So money has doubled when the amount A is twice the principal. In other words, the balance is twice the principal. So the balance is going to be 2p, 2 times the principal. So now I could just say 2p is equal to p times e to the 0.065 t, y 0.065, because that's 6.5% as a decimal. But notice I have p and p, the p's cancel. We divide both sides by p and they cancel. So you see, it does, since the p's just cancel out right immediately, that's why it didn't matter if the p was $1, $1,000, $20 billion, doesn't matter. Now I just take the log of each side, the ln of each side, the natural logarithm of each side, and then do some algebra like I did before, and I get t is equal to ln 2 divided by 0.0065, which comes out to be 10.6 years. So if you invest money at 9%, after 10 years it will double. It's kind of cool. And that concludes section 3.1. It's been loads of fun, and we'll see you guys next time. Bye.